Okay. Which questions do you want to start with in section 3.4 homework? Number 71. We're going to jump right into the word problem. All right. Let me. All right. So number 71, okay, you're given this supply-demand relationship. They gave you that the price is equal to 3,000 minus 1/2 x. Oh, yeah, I have to actually be showing you what I'm doing. That would be unfreeze. Yes, I am now videoing. So, all right. Now let's talk about what they're actually giving you here. We have been doing equations like this in Algebra 1, in geometry, it's no big deal. Except now, let me ask you a question. What's your input? X. Your output is P. Is P a function of X? Okay, what's the definition of function? For each X, there's only one Y. So each time I put in X, which is the number of units, do I only get one P price back out? Okay, so it's a function. So P is a function of X. Because, and we have this set up that this is typically your output, this is typically your input in this problem. Could I, if I so desire, rename this as P of X? Because it is a function, I can use function notation. So a lot of times we kind of have this handy dandy little idea that we can write it this way. Now, what if I were to take this equation and solve for x? Okay, so P minus 3,000 times 2. If I subtract, is it times 2 or negative 2, okay, would equal x. Now, this idea of me solving for x, what I have essentially done is switched my inputs and outputs. So now I ask the question, is x a function of p? Because now we're considering in this solving process that this is the input and this is the output. Could I rename this if I so wish? What could I rename this as? X of p equals negative 2p minus 3,000. All right, everybody okay so far? They also gave you in this problem, so that was just playing around with that, do a little pre-work for it. They also gave you in the problem that the cost as a function of x, the number of units, is 2,000 plus 10x. Okay, so I input the number of units, I get out the cost. Now what they ask you to find in A is they want you to find the cost as a function of p, which means they want your input to be p and your output to be cost. Now, how do I take what I already have and somehow get my cost function, which right now has an input of x, to not be an input of x, but to be an input of p to start with? The x of p function. If I were to do cost as a function of x of p, basically I'm just renaming this, okay, into this. And that is C of P. That's what my point is going to be. That really, what is this resulting in? Once I get the composition, I create this new formula, 2,000 plus 10 times our x of p, which was negative 2. I'm going to distribute this, just negative 2p plus 6,000. So negative 2p plus 6,000. Once I plug this in, I basically got a new formula. What's my input into this new formula? P. What's my output? See, at the very end, even though I might have had to go through X in the middle, I basically created cost as a function of P by using that relationship. Okay? And so this, if you want to simplify it, what is it? 8,000 minus 20P. Yeah. Oh, that would be helpful. Arithmetic. I know, I'm videotaping and I showed how bad my arithmetic is. 60,000 plus 2, 62,000. There you go. Minus 20p. It's 10 times, that's what we were saying. 10 times 6,000, 60,000, add the 2,000. All right. What do you mean related? They say that the input for these X is referring to the number of units for sale. They've defined it in the problem, and every time you see an X, it's referring to the number of units for sale in this problem. Okay? Yes. Yeah. Is this enough to help you answer the rest of them? So it's pretty much, you've been doing substitution all along. Even if I didn't call these functions, if I had a relationship between P and X and a relationship between C and X, which, aren't you basically just doing substitution? And basically rearranging, combining the two together so that you get the input you want and the output that you want. That's all you're doing. Okay. But you need to understand that this is composition. That's why it's in this section. All right, what number did somebody just ask? How would you do C? All right.
Revenue would be like cost minus, and then you have
Well, yeah, profit, is it profit? It's revenue minus cost. Revenue minus cost. Yeah, so you basically, because in part B you did revenue, same idea. And then your revenue minus cost. So once you have A and B, you just take B minus A and then you get your answer. Okay. All right, what was the number? 74. All right, in 74, our pool volume, we have a 20 by 10 rectangular pool that's going to be built. Draw myself a little rectangle. Oh, and I'm in 3D. Why am I in 3D? Because I have depth. Okay. So I have a 20 by 10 by some, I'll just call it height, depth, height, whatever you want to call it, height pool that we are going to be looking at. And it's 50 cubic feet of water is pumped in the pool per hour. So 50 cubic feet of water per hour is being pumped in. And we want to write the water level as a function of time. Water level, and what did I call water level? H, as a function of T. All right, well, first thing, do you know something about volume of this pool? Okay, so volume equals 200H. I know, but what does this give me? This gives me a function where volume is a function of H, okay? So I'm writing down things I know from the problem. Can I figure out my volume as a function of time? Like, how do I know how much water we're going to have in this thing volume-wise? Yes. Per hour.
That means that the volume is 50 times the number of hours.
All right, so we'll do 50T. So, why not? Well, I haven't got to the height yet. I'm not done. You're right, I'm not done. All I have done at this point is write down a volume as a function of height, and I have written volume as a function of time. Now what I want is height as a function of time, and I want to combine these together in some way. Maybe, because I want height as a function of time, what if I wrote this like H equals volume over 200? Now I have height as a function of volume, and I have volume as a function of time. Oh, do you see how I have a little transitivity going here? If I do height as a function of volume, which is a function of time, there's my composition, I will end up with the input I want and the output I want. So how does this end up working out? What's my formula? Divided by 200, and you can simplify t over 4, and then that would be our formula that we are looking for. So at the end result, height is a function of time. Right? Other problems from that section? Anything else? Was that an I'm thinking, or an no, I'm good?
I got it.
You're good? Anything else? All right, so now let's take a look at the new notes. So kind of leaving 3.4, now that we understand how composition is, and talk a little bit more about some uses. And we're going to start with a little class opener because I thought it would be nice to remind ourselves this is going to be an important skill that you need to have. I want to calculate f of g of x and g of f of x using these two functions. Okay? And this will be also helpful because it'll remind you of what work you should be showing to me on these on a test or a quiz. All right, so I'm going to start with f of g of x. Okay, the first thing you have to show me is what you substituted in. This, you don't get to simplify in step 1. In step 1, you show me the substitution. Which function do I look at first? Well, g is going to get plugged into f, but remember, I always start with f. What's f going to be? 3 blah plus 2. So I kind of go to the outside first, and then I say what gets stuck into g or into f over 3. So the first step, you must show me your substitution. Then the rule is you are only allowed to cancel one thing per step, because I'm checking on your order of operations. You'd be surprised at how many people can't understand what cancels first. What cancels first in this? The 3's. So you are allowed to go x minus 2 plus 2. These aren't so bad. And then your 2's cancel and you get x. Okay? We haven't done domain. Maybe I should talk about domain. What's the domain before I simplify? Right, because it's got a fraction, but the fraction doesn't have a variable in the denominator. So we'll do domain of f of g is real numbers. All right, and then I'm going to do g of f of x. All right, now in that one, what do I start with? G, which is blah minus 2 over 3. What gets plugged in? 3x plus 2. So you show me the substitution. Then we start to cancel. What cancels first? Plus 2 and the minus 2. Leaves me with 3x over 3. Then your 3's will cancel and you're left with x. Now, you had several of these for homework. Does that mean that every time I do f of g of x and g of f of x, I get x? No. There must be a reason why we keep looking at these functions that happen to end up being x. They are inverse functions of each other. F and g, oops, can't spell, f and g are inverses of each other. Now let's remind ourselves what an inverse actually means. Let's go back to chapter 0. Okay? Chapter 0, I have a number x. What is its multiplicative inverse? 1 over x. And when I combine the number and its multiplicative inverse of the operation of multiplication, I get 1, which happens to be the multiplicative identity. Okay, right? Properties of numbers. If I do x, if I do the operation of addition, what is the additive identity? negative x is the additive identity. Additive inverse. And you end up with 0, the additive identity. So when I combine something, an object, with its inverse, I get back the identity. All right? What operation am I doing now? Composition. I am combining objects, which happen to be functions, using composition. Composition is the operation. And when I do this composition operation of a function, and yeah, remember your parent graphs? What did we call the parent graph y equals x? Oh, the identity function. Oh, hey. If I put two objects together that are inverses, I end up with the identity. I'm doing the same thing but in functions. And notice that technically x times 1 over x is 1, and so is 1 over x times x. That you have that, what property? Commutative property has to work. And negative x plus x, that you have to do it both ways. Okay, even if we don't write it. That's why we have to do f of g and g of f. We have to make sure it works both ways in order for it to be true identity. Yes? Right? Any other questions? All right, so now it's down here. Before we actually get into a lot more discussion on these inverses, I should finish my sentence, of each other. Before I get to more information about inverses, let's talk about how do we know that we're going to have functions that, the idea is the inverse will undo what's been done. Okay? Think of it like this. Look at what we have up here. F takes a number, multiplies it by 3, and adds 2. How do I undo that? Minus 2. And, oh, see how they are reverses of each other? It's kind of almost like sad map. Yes?
Okay. When you do x times 1 over x, don't you lose the restriction?
Yeah, we're assuming that we're talking about objects.
Okay.
Of the objects that are possible, they have an inverse,
Okay.
right? So I said we started with real numbers, and if x was 0, would I have a problem?
Yeah.
Because 1 over 0 is not a real number. So I'm within my objects that are allowed, okay, then I have to worry about it. I have to actually have real numbers in order to do this, okay? And yeah, you are right. There are problems that you have a x cannot be 0 in this problem. There's no restrictions over here, but on that one you do. There are functions, yes. So hold that thought. All right, so let's go down. We're basically we want to talk about, and this goes to your question, there are some functions that do not have inverse, an inverse. Okay, I'm going to say it that way, an inverse. I want to know which functions have inverses. I want to be able to put in a number, do stuff to it on one function, take the result, put it into another function, and have that function undo it and give me back the number I put in. I want that to happen every single time. Okay? Yes? The imaginary number I? Yes. All right. So now, let's not get too antsy about this little. This is just trying to give you a small discussion of a property that I want to. We've already discussed this property. Let's not get into this whole argument about the whole sciencey kind of thing of this. Okay? So let's just focus on the math, the kind of reasoning. I'm preempting the comments that I know are going to come. So I'm just going to tell you right now. All right. First thing is we remind ourselves that to have a function, each input has to be mapped to exactly one output. I put in an input, I have to get out a unique output from it. Okay? So, leaving math behind for a second. I have every human being has a unique blood type. Leaving math behind for a second. What would you consider your input? You input your human being, whoever it is, and what does your function look for and return as the output? The blood type. Now, my question is, for this to be a function, I'm basically trying to say, is blood type a function of the person that you're putting in? Is your blood type, do you get one blood type for each person you put in? If I go to the doctor, me, and I say, here's my blood, type it, will I have more than one blood type, or will I have one blood type? One. Okay, so this is a function. I said leave the extraneous details out. We're going to go for this. Right, so since I'm talking about the human having something, I'm putting in the human and saying, what do they have? Okay? All right, every human has a unique DNA. So again, we're going to input the human, and we're going to output their DNA sequence. Is this going to be a function? All right, now we go more mathy kind of thing here. I put in a real number on the number line. I'm on the X number line. I put in pick a real number. 2. How far is that from 0? 2. Okay, I put in -3. How far is that from 0? 3. All right, so if I input a real number and I output the distance from 0, is that a function?
No. Yes. No.
Is -3, why did everybody say the same answer? I said, I put in -3. How far is that from 0?
3.
It's 3. I put in a real number and asked the question, how far from 0 is that number? Okay? That's not absolute value yet. I put in a real number and asked for distance. It's a function because every number is exactly one distance from 0. Function. So y'all are trying to do it the other way around. I haven't gotten to that point yet. I'm saying, is this a function? I put in a real number and I ask, how far from 0 am I? You will always give me one answer.
Let's get through a little liturgy.
All right. I put in a degree Celsius and ask you how many degrees Fahrenheit you get. It's a function. Okay. Function. Oh, well, you get it. I mean, degrees Fahrenheit, degrees Celsius. There we go. I like it that way. Now, once we have a function, we want to start trying to look for a property that's going to give us this idea for an inverse to exist. A function that will undo what I have done. I want it to take my output and map it back to the input that I had. Okay, and this is a function called a one-to-one function. Okay, and we've talked about this property before. Now, coming back up here, we want to go the other way. Right now I know that blood type is a function of the human being that I put in. If I put in a human, I get one blood type out. If I put in a blood type, will that map directly back to one person? No, there are many people who have the same blood type, okay? So this is not a one-to-one function. There is not a one-to-one correspondence between a person and a blood type and a blood type and a person. Otherwise, we'd have to have millions of blood types. No. We're saying each human I put in, each person has one blood type. Okay? And now I put in... No. Imagine that. The math teacher trying to be biologically sound. Thank you, Charles. Okay. So going the other way, it doesn't work. Now, so what that means is there's not really a inverse function that will exist that says, hey, I know the blood type was this, A. I can tell you who it was. Can't do that. Okay, that means there's not going to be an inverse for this. All right, let's go to the second one, B. Every human has a unique DNA, so you input humans, you get out your DNA, and we said DNA is a function of the person that I put in. Is the person you put in a function of their DNA?
Yes. Yes. Yes.
What makes me brother?
Oh!
Okay.
No, no, not DNA. They have a different thing here. Oh, you all.
Okay. Okay, so for most people, is there a one-to-one correspondence between DNA and who it is? Okay, now for twins, I will say somebody showed me some research last time where they were talking about how environment changes your DNA once you're born. And that the twins, while they're very, very close because of the genotypes, they are not exactly the same. So I'm going to go with, yes, this is a one-to-one function. They have their own experiences. According to this little study, New York Times, we researched it and whatever. I'm not going to get into the whole debate over it. We're going to say, in the math world, yes, one-to-one. Otherwise, how could they use this to convict you of a crime?
What if you got your twin brother to convict you? What if you got your twin brother to do the crime, and then your twin brother turned on you and made you seem like the guilty one?
Then you got some trouble.
Was the one that investigated your case, and then
All right. Focus back up here. Focus back up here. All right. What about the distance on the number line function? Okay, so I have distance as a function of the number I put in, but is the number I put in a function of the distance?
No.
Because if I tell you the distance is 3, what number did I put in? 3 or negative 3. So it's not a function. The other way around. So this is not one-to-one. Which means that we're going to have problems when we start trying to undo things, because I don't know which one I actually put in, the 3 or the negative 3. Yes?
Doesn't this kind of go back to the conditional statements? Like B would be by conditional.
Oh, you're trying to say that
Like,
if the human has a unique blood type, then the unique blood type must have a unique human?
no, sort of like, if it's a human being, then there's a unique blood type.
If there's a
It's
unique...
blood type, it's not necessarily a human being. It's not by conditional, it's not one one.
Yes. Kind of idea. Okay?
All non-one-to-one functions cancel the biconditional because you can say.
Like if I was doing a mapping, like in this one, I know that 3 goes to 3, right? Number 3 goes to a distance of 3. Negative 3 goes to, oh, wait a minute, why do I want to write it again? I already wrote it in the list. So when you look at it in the mapping, you actually just go negative 3 goes to 3. Each x has exactly one y. It only points to one thing. But when I'm on this side, does each y point back to 1x? The answer is no. So it's not going to be one-to-one. If it was a truly one-to-one function, like here, degrees Celsius, degrees Fahrenheit, degrees Fahrenheit, degrees Celsius. That one is. That if I know 0 degrees Celsius is 32 degrees Fahrenheit, is 32 going to go right back to 0? Yeah, so it's a one-to-one correspondence, no matter what I pick. 100 degrees Celsius is 212, and 212 is 100 degrees Celsius. There's no... Yes?
So, a one-to-one function would be something where it would be like on a graph, it'd be for every x value, there's no y value. For every y value, there's exactly one x value.
Yes.
But if it's a function, it would be for every x value,
There's one y value.
but for every y value,
There may be
yeah.
more than one x value. Maybe more than one. For one-to-ones, you can perform it. There must be input goes to this. This goes right back. If and only if. Okay? All right, everybody good? And again, why are we doing this? Because we want to make sure that we understand that inverses only exist if you have a one-to-one function. Okay? So we'll talk about what happens when you don't have a one-to-one function shortly. But you gotta have to have an inverse, a function that will completely just undo it. Whatever I did, you have to have a one-to-one function. All right, now, talking about implications. Let's talk about, geometry. P implies Q. If P, then Q, right? If P, then Q. Okay. Name another conditional statement. Negative Q, then P. What do we call, then not P? What do we call that? The contrapositive. Contrapositive. What else could I do? If Q, then P, which is the converse. If not Q, then not P. Then I did Q implies P, which is converse, and then not Q, that's the inverse. Okay? And do you remember from geometry which of these are equivalent to each other, that mean exactly the same thing? All right, so, oops, that's not what I wanted to do. So these two are equivalent statements. They mean the same thing. They are true in exactly the same cases. Right? The example that I would use, if everyone gets 100 on the next test, I will buy you a Sugar Shack donut.
Is that true or like?
Okay, I'm making a statement. Okay? I am making a statement. If everyone gets 100 on the next test, then I will buy everyone a Sugar Shack donut. Okay? All right, for that to be a true statement, okay, let's talk about when that is true. All right, so suppose everybody got 100 on the test. So P is a true statement. Okay? And I bought you donuts. Did I tell you the truth with my statement? Okay. What if P was true, everybody got 100, and I gave you a thumbs up, but I didn't buy you donuts? Did I lie to you?
Yes.
Yes. Okay? So P implies Q was true there, false there. Okay? Don't change it. Don't change my original statement. Just don't change my original statement. Let me finish my thought with the statement that I'm working on. Okay? Now suppose that you guys did not meet the requirement of getting all hundreds on the test. And I didn't buy you donuts. Okay? Did I lie to you with my statement?
No.
Okay, so the statement is still true. All right, what if you didn't succeed in the 100, everyone get 100 on the test? I bought you donuts anyway. I felt sorry for you. Did I lie to you? Did I?
No.
I said if everyone got 100, then I would buy you donuts. Did I ever say what would happen if you didn't get 100? No, so I didn't lie to you. My statement was still true. I said if you get 100, then I will guarantee that I will give you donuts. But I never guaranteed anything about the reverse of that. Okay? So this is still a true statement. All right? Now let's look at the contrapositive. All right, so I was, if you get hundreds, then I buy you donuts. What do you mean false, true, true? P, false, Q, true. My P implies Q statement, still true. Didn't lie to you. I'm only talking about this. Okay? All right, now let's talk about not Q implies not P. In my scenario, what's not Q? I did not buy you donuts. So if I did not buy you donuts, then you did not get hundreds, everyone get hundreds. All right, so what's not Q? Look, can I do the same 4 cases I have up here? So I can go false, true, true, and false. What's not, I'm going to do not P over here, since I like to go in that order. All right? Not Q, or not P, sorry, would be
Not getting something.
false, false, true, true. Just taking my cases I had up here and then writing down. All right, so let's talk about not Q implies not P. I didn't buy you donuts. You didn't get hundreds. Did I lie? Did I tell you the truth? Truth. Okay? I bought you donuts. You didn't get hundreds. Is that true?
If we didn't get,
I promised that if you got hundreds, I would give you donuts. Okay? You didn't get donuts, but you got hundreds.
oh, no, that would be false.
False. Okay? Alright? If you didn't get donuts, and you didn't get 100, is that true?
Yeah.
It's still true. And not Q. If you got donuts, it's like a double negative. I'm trying to go double negative. If you got donuts, but you didn't actually get the 100, did I lie to you?
No.
No, because I made no promises about that. What do you notice about these cases? They are equivalent. They are the same. Okay? So the implication and the contrapositive are equivalent statements to each other. However, is the converse equivalent?
Not always.
Never.
Oh, whatever.
Okay? To be equivalent, in every possible case, they have to have the same truth table, truth falseness. Okay? Equivalent. In every case, they have to be equal to each other, not equal in every case. So these two, they're actually equivalent to each other, because isn't the inverse the contrapositive of the converse? Ah. These two are equivalent, but this pair is not equivalent to those. They mean different things. All right, so this whole conversation is, there are two ways to get a definition of one-to-one. The first one is basically saying that if I have two elements in the domain that are not equal to each other, what can they not share? They can't have the same y value. That's what this is saying. If the x values are different, then the y values have to be different too. They can't have the same y value. Because if they had the same y value, I would get the situation like we did in the real number line, where I go two different x values go to the same y value. So that's one way of looking at the definition. What would be the contrapositive of this if-then statement? If f of x2, then x1 equals x2. That means the same thing. Now what does that say? It says if the y values are equal, the x values have to be equal if it's a one-to-one function. Because if the y values are the same and you have two different x values, then you throw out your one-to-one correspondence. Okay, you look puzzled, Charles.
Not always.
You feel like it's more complicated than what it sounds like? No, it's not.
Wait, is this like the inverse thing we just did? This is totally different.
I'm just talking about this is definition of one-to-one.
Yeah, I get that.
That's all I'm doing.
Okay, that's all it is. Okay.
That's all I'm doing.
I'll let
Okay?
it go. I'll
Okay.
let it go.
All right, so let's come down here. Let's talk about, remember your rule of 4? We look at functions numerically, graphically, algebraically, and verbally. So, my definition I was writing up here, this is really your verbal representation. What are the two statements that we're looking for? Then we come down here to these points. This is your numeric points. Okay. All right, first off, is this a function?
Yes.
Each x has exactly one y. If I look at a mapping, 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, and 5 goes to 6. This is a function. Is it a one-to-one function? If I look the way I've drawn my mapping, each arrow goes directly over, and then if I wanted to go backwards, could I kind of go, hey, it works both ways. 1 goes to 2, 2 can go back to 1. Okay? So this is a one-to-one function. All right, is the second scenario a function? Now, I have 1 going to 2, 2 going to 3, 3 going to 4, 4 going to 5, 4 going to 6, and then 5 going to 7. Does everybody see how you have one x value that has two y values? So it's not a function. Not a function. We do not consider one-to-one property unless you actually have a function to start with. Okay, so this is not a function. We don't even consider one-to-one. Okay? Then we come over here. Yes.
So only functions can be one.
Yes. Because we're trying to figure out if a function has an inverse that will undo it. So if I don't have a function to start with, then we're out of the game. Okay?
If one-to-one, then function, but if function,
All right.
not necessarily.
Third example over here. Okay, is this a function? 1 goes to 4, 2 goes to 1, 3 goes to 0, and then 4 goes to 1, and 5 goes to 4. So it's a function, but it is not one-to-one. So I'm going to have some issues going backwards. And basically what we're looking at this, if I were to explain, okay, why this is a function, each x has exactly one y, and each y has exactly one x, if I had to explain it. Over here, why is this not a function?
Oh, that one? Oh, because for each x value there is more than one.
Yeah, can we be more specific? Because I don't really need to keep going general for this. Why is this one?
X equals 4.
Okay, x equal to 4 has 2 y values. They're done. Doesn't matter how many I have. I only need to have one x that has more than one y. We're not a function. Over here, am I a function? Yes. Each x has exactly one y, but what's the problem? Just name one of them, because it only requires one counter example. Y equal to 4 has 2 x values. That's why it is not one-to-one. All right, everybody good? Graphically, how do I determine if I am a function?
Vertical line test.
Vertical line test. How do I determine? Well, he's showing the pencil going up and down.
Did I?
Okay, just drop.
You just did.
You have to do it for all x's. Okay. Vertical line test. What about one-to-one function?
Vertical and horizontal.
They're all from
Yeah, vertical must be met first, and then you do a horizontal line test to see if it is a one-to-one function. So the answer here, is this a function? Yes, but not one-to-one. Is this square root a function? Is it a one-to-one function?
Yep.
Yes. Your cube root, function, but is one-to-one. Notice my little shortcut for one-to-one, so I don't have to write 1, 2, 1. This is your f of x equals 1 over x squared. Okay. Function,
Not really much to say.
one-to-one. not 1 to 1. This is our function 1 over x, 1 to 1.
Yep.
Function 1 to 1. Absolute value, function not 1 to 1. All right, see, nice, easy. So we've done the verbal description, we've done the numeric description, we've done the graphically. What's left? Oh, darn algebra. All of the methods we have so far are kind of a description, but they're not really proof. Because me looking at, even if I had, the only way to do numerically is if you had every single point, and you could examine every single point on the function and see that each x goes to 1y and each y goes to 1x. But most functions don't have a finite set of points. You could disprove it. You could prove it's not 1 to 1 numerically very easily by showing one y value that has 2 x's. That's a good point, okay? So we can disprove 1 to 1 by looking at a table of values as long as we happen to luck out and have a y value that has 2 x values. But maybe we don't luck out because we have this infinite set of points on the function and maybe I don't have enough of them to determine. The more points I list, the more my belief is that it's 1 to 1. Right. You can reject it, but you can't prove it true. Because to prove true for all, is there any way on a function that has infinitely many points to actually look at every point and make sure you're okay? No. So we get belief, but we don't necessarily get proof. Sort of, yes. Okay? All right. If I'm looking at it graphically, we would hope that the picture that we have is representative of the whole behavior of the function. Okay? So we get belief that we are 1 to 1 or not 1 to 1. The not 1 to 1 you can definitely get. But to know that this is 1 to 1, what do you kind of have to know beyond the border of the graph? That it kind of continues in the fashion that it has been. Now, does that prove, just me looking at this little picture of it, does that prove that it's 1 to 1? No. The bigger I establish my window, the more belief I have that it's 1 to 1, that it's going to continue the pattern, but it doesn't prove it. Okay? To prove it, you always have to go by algebra, by the math. Okay? Now, proving a function is 1 to 1. These little proofs, they're very formulaic. It's very nice because there's not a lot of difference between them. Each time we do this, we're going to go back to this definition, this implication. And this is kind of an idea that this is how you prove all if-then statements. The if-then statement says, if this is true, then this must be true. So the way that you prove all implication statements, all conditionals, this is kind of like going back to geometry a little bit. Step 1, you state your given, which pretty much in these are, what function are you given? So you tell me what f of x is. State your given. There will be times where we skip this step because we assume that if it's written in the problem, you understand that we gave you this function. At the beginning, we're going to write it, but we will get to the point where you kind of skip that step because you're like, it's written right there. That's what they gave you. All right, here's the most important step in this conditional proof. You always assume the hypothesis is true. This does kind of play a little bit in your statistics. Because do I care if the hypothesis is false? What happens?
It's not a function.
It's not, don't think about function, just think about the true falseness of the implication.
Then the original.
I'm just trying to figure out that if this happens, does the conclusion happen? Does the then part happen?
Well, if the hypothesis isn't true, then you can't.
Well, if the hypothesis isn't true, then that doesn't have any bearing on this statement being true or false. I really need to say, look at the case where if the thing is true, if the hypothesis is true, then, right, or true, we don't care. We don't care because I'm not lying to you. Right, so the only case I worry about is where the hypothesis is true. So I assume it's true, and then so that's kind of the first step of every proof for an implication. You assume the hypothesis is true, and what you want to do is combine your given and this step together, which means we're going to do some substitution. whatever your function is. If f of x is x squared, that's your given, okay? And so you combine these two together using some substitution, and what you need to show is that x1 equals x2. You have to show the conclusion results from those two pieces of information. Everybody good? All right, let's show you how this works. Now, there will be times I'm going to tell you it might be better. I'm using x1 and x sub 2 because are those the same x value or different x values? They are different. And for some reason, that confuses students. So I am going to kind of, over here on the side, go, I'm going to call x1 A, and I'm going to call the second one B. For some reason, this helps students when they do these types of proofs, because they're like, clearly I have two different numbers, okay, that are not equal to each other. All right, so I'm going to, when I do this, I'm actually going to do f of A equals f of B as my assume part. And then I'm going to ... show that A equals B. That's my target through this. All right, so let's do the example. And like I said, we're going to make you write the given and all that stuff here. We'll start shortcutting eventually, but right now we're not. So I want to prove that this function is one-to-one. So given, it's the easiest point you earn on a test. F of x is 5x cubed plus 3. Now, do I have any belief that this function is one-to-one? It's a cubic, we'll draw on Travolta, with a vertical stretch of 5 and a shift up of 3. So just picturing the graph in my head, I have belief that I'm one-to-one. Okay? I am going to assume f of A equals f of B. Which, what does that mean? It means I'm assuming the y values are the same for an x equal to A and an x equal to B. I'm assuming the y values are equal. What does function notation, what's f of A mean? Now here's the actual meat of the proof. You plug in A into the, for every x. So do you see how I said combine the two together? All right, plug A into the function you were given. That would give me 5a cubed plus 3. Now plug in b. 5b cubed plus 3. Now I'm going to do a little algebra. What is my goal? A equals b. Rule, just like it is when you did the whole f of g of x thing, is one simplification per step. What would I do first? Subtract 3. So 5a cubed equals 5b cubed. Then I would divide by 5. A cubed equals b cubed. Then I would cube root both sides. When you cube root, is there any issues that we had? No, cube. Not in real world. Well, not even in imaginary world. We're okay. But we're in real world. We're in real world. Just leave the imaginaries behind. So we have a cubed. Cube root, what do I get? Oh, a equals, yay! That was my goal, right? Right, it's easy. These proofs are super easy. It's because we had belief anyway it was one-to-one. If a function is one-to-one, this beautiful little thing always works out nicely. If a function is one-to-one. Now, typically we're not done with the proof until we write a statement concluding what we did. Okay, what did we show? We have shown that if the y values are the same, if the y values, f of A and f of B, are equal, then what did we show? The x values, A and B, are also equal, which means the function is one-to-one. By definition, basically, f is one-to-one. Okay? That's the full formal, completely written up, everything you're going to write. But we do start to shortcut. Because you're like, okay, what are the most important steps here? You guys are always going to write the given. You're going to do this. You're going to do this. As long as you understand this part, we'll just go, what's the symbol for therefore? The 3 dots. We will go dot, dot, dot. F is 1 to 1. We will skip over, the big sentence that's really explaining what I'm doing and just go, hey, therefore, F is 1 to 1. This is why I'm allowed to do that, but we're like, as long as you get that, we're like, hey, by definition, F is 1 to 1. All right, everybody good? All right, let's look at our square root graph. Do we have a belief that the square root graph that went to the right one is probably going to be 1 to 1? All right, so I have a belief, so I'm going to start my proof. Given f of x equals square root of x minus 1. All right, now before I do this proof, I want to add something up above. Okay, everybody look at me. This definition that we had, this if statement, what has to be true since I'm plugging things into the function? What has to be true about x1 and x2? They have to be in the domain of f. Otherwise, you can't plug them in, right? So that's kind of understood in this process, that I have to start with x values in the domain to be able to even plug them in to start with. Okay. All right, so keeping that in mind, what's the domain of f?
1 bracket
1 to infinity. So when I am choosing my a and my b, a and b have to be from 1 to infinity on this. This is going to be important. You don't really need to write this down. We're just kind of in our head talking right now, saying, hey, I remember that I can only plug in numbers bigger than or equal to 1. And so the values that I am going to assume, so we're going to assume f of a equals f of b. And we're going to keep in mind that this a and the b that I am plugging in have to be from 1 to infinity. All right, now what do I do? What's f of a? Square root of a minus 1. What's f of b? Square root of b minus 1. All right, and what are you going to do as your first step? Square both sides. Now this is why the whole thing is important. Let's kind of recall our chapter 0. The square root of x squared. What's the domain of square root of x? 0 to infinity inclusive. You want to simplify that. What does that simplify to? No, it's not absolute value. X.
where x does not equal, or yeah.
Where x is non-negative, or we could say where x is greater than or equal to 0. We want it to not be negative. Okay. Remember, you have an exception for this, or you could say instead of where x is greater than 0, you could say except when x is negative, right? That's the other way to say that. All right, so it has an exception. So this is only equal to x when x is in the domain. It's another way of saying it. But what do we know about this right here? What did I tell you about a? It's in the domain, otherwise I can't do it. So if I want to square both sides, here and here, to get to the next step, can I write this as a minus 1?
You could say that, yeah.
Because what do I know about a? We already established a is in the domain. If a is in the domain, it's going to be a minus 1. If b is in the domain, then b minus 1. Okay, so I'm only using it because I don't have to write the exception, because I know that I can't use them unless they're in the domain. If they're in the domain, then I don't have to worry about writing the exception. I already know they're in the domain. And then so we can go, oh, a equals b. Therefore, f is 1 to 1. Okay, everybody good? You see how formulaic these are? Pretty much just memorize the format. This is the easiest proof you ever have to do. Let's do one more. All right, given f of x equals negative 2 x minus 3 cubed plus 1, I want to assume f of a equals f of b. I don't care. Once I get to here, what's f of a? Minus 3 cubed plus 1. F of b. Oops, b. All right, what do we get rid of first? Minus 1. So minus 2a minus 3 cubed minus 2b minus 3 cubed. Now what do we get rid of? The negative 2. A minus 3 cubed, b minus 3 cubed. Cube root. Cube root, okay, I don't have any issues with that one. All right, what's the only time we have issues on these things? Even roots, okay. All right, so this one, okay, take the cube root. I get a minus 3 equals b minus 3, and a equals b. So I told you they work out, if it's 1 to 1, and we have a belief it's 1 to 1, this works out very nicely, always. Therefore, f is 1 to 1. Yes?
I don't understand why this works. Like, how would you have an equation where it wouldn't work?
All right, we're going to do that right now. All right, now notice I did not ask you in example 4 to prove that it is 1 to 1. Because let's think about our parabola. What do we know about our parabolas? They have 2 halves and they're going to fail a horizontal line test, right? Now, I'm going to show you what happens, but I'm never going to try to disprove 1 to 1 this way. Because really, to disprove 1 to 1, all you have to do is find a y value that has 2 x values. That's going to be super easy, okay? This is just showing you what happens, to answer your question. What happens if I try to do this, prove it's 1 to 1? Maybe I don't know what a parabola looks like, and I just am, plugging and chugging, following the steps to do this. All right, so if I say that I was given f of x equal to 2x squared minus 16, and then I assume f of a equals f of b. So I'm going to start out the same way. I'm like, okay, what's f of a? 2a squared minus 16, 2b squared minus 16. You're like, hey, it's all the same. I add 16. 2a squared equals 2b squared. I divide by 2. I get a squared equals b squared. And then here's where I have a problem. Let's remind ourselves. What's the square root of x squared? Absolute value of x. Right? So I go to square root both sides because I'm trying to get rid of this, and I'm not going to get to a equals b. I'm going to get to absolute value of a equals absolute value of b. And then I go, wait a minute, what does that mean about a and b? Either they are the same or they are opposites. And right there, I have a problem. I didn't get a equals b. I got a equals b or a, oh, that's because there are 2 y values that go to a, or there are 2 x values that go to a y value. So I have a problem. I would never do this to actually disprove this, though. This is just me showing you what's going to happen. Well, you could, but it's long. I want to do the short way. The shortest way is to recognize that when you have a function that you're pretty sure is not 1 to 1, all you have to do is find a single counterexample. Because to disprove for all, you just got to find one thing that doesn't work. And we don't even care which one you find. Like in this, we're saying y equals 2x squared minus 16. We need to find a y, and usually you try to find a nice one. We want to find a nice y that has 2 x's. Sometimes I do this to kind of help myself out on finding a nice one, because I need y plus 16 divided by 2 in order to be a nice perfect square, just so I can get a nice one. Maybe I'd use y equal 2. 8, that would give me square. I want a nice one. I would do 2. Because 2 plus 16 is 18. 18 divided by 2 is 9. Okay? That's just me trying to get a nice one. You don't really need a nice one, but it always is good to have nice numbers. So we would say if y equals 2, then what is x squared, or what is x equal to? So if I put a 2 in here, that would be 9. So x equals plus or minus 3. So f is not 1 to 1. All you have to do is tell me a y value that has 2 or more x values. We're done. We walk away. Yep, we've disproved it. All you need is this. Tell me a y value and its corresponding x values that throw me out from being 1 to 1.
Can you use the therefore?
Yeah, you can go therefore instead of so. That's fine. All right, so like same thing down here. This work over here is just you trying to figure out a nice one. And I do the same thing here. I kind of go y minus 1 divided by negative 3 equals, I kind of isolate the perfect square because this is helping me figure it out. And I go, what would make this a nice perfect square? What y value? What would be a good y value to get this to be a perfect square? Pick a perfect square.
-2.
Yeah, negative 2 minus 1 is, yeah, I mean, in your head, aren't you just basically going, hey, I want that to be something like 1? Or 9, and then say what y value makes that happen. So when y is negative 2, if y equals negative 2, then what are the x values? Again, this is just my scratch work trying to figure out my x values. What do I get? 4 plus or minus square root of 1, which is 1, which would give me 5 or 3. Then x equals 5 or x equals 3. Therefore, f is not 1 to 1. Does it matter which y value you pick? No. You just have to get 2 of them. 2 x's to go with it. All right, what about example 3? Oh, it's an absolute value. Does it really matter what number I pick for y? In this case, it's not like the parabola where I have square roots. Just pick a number. What do you want to pick for y? If y equals 1, then, all right, if I put 1 in here, let's do a little solving, because I got to figure out the corresponding x's. Well, maybe 1, if I subtract 2, that's going to give me negative 1/3. I'm not a big fan of fractions. Let's do, I know, but we want nice numbers.
Wait, but negative 1/3 equals the absolute value.
Let's make this, I know, let's do 5. I like 5. Because when I do 5 minus 2, I get 3. I divide both sides by 3, I get 1. How do I solve absolute value? X minus 5 equals, come on, remember chapter 1. 1 or x minus 5 equals negative 1. So x is 6 or x is 4. Okay, then x equals 6 or x equals 4. Therefore, f is not 1 to 1. You just have to find the counterexample. Yes.
If you did 1, you got negative, what was negative 1/3?
If I did
If you
1,
did
yeah, the problem is then
yeah.
I have no y values, and that's why I was throwing it out, because I went, oh, wait a minute. You got to actually have a y value on the graph. Now, if I'd been smarter, I would have looked over here and said, what transformations do we have? We took the absolute value, we went to the right 5, stretched it by 3, and then went up 2. So if I went right 5, stretched it by 3, and then went up 2, it's over here. What are the only y values I should be picking? Anything 2 or higher. Can I pick 2 as the y value that I want to use? I can't pick 2 because I need to have 2 x values, and that's the vertex. That's not going to work. So I got to pick something other than 2. All right, fine. It's over here. It goes right. I said right, but then I drew it left. I don't know why I did that. All right, there we go. So I'm over there. All right, everybody good? Now, inverse functions. All right, you only have inverse functions for functions that are actually one-to-one. We'll talk about what happens when you're not one-to-one shortly, but you only have inverse functions when you are one-to-one. So now that we've learned how to determine if a function is one-to-one, if it is one-to-one, then we know that there is a inverse function, a function that will undo whatever happens. Okay? Now, remind ourselves here that because of our property of inverses and identities, that if I put together your function with its inverse under the operation of composition, I get back the identity, and it has to work whether I combine them F to G or G to F. Okay, it has to work both ways, otherwise we have issues. All right, so suppose, let's look down here numerically. I have given you two functions, and these are the only points on the function. Okay, the only points on the function. I know that 1 goes to 2, and 2 goes to 1 over here. So that seems okay, right? 1 goes to 2, and so 1 went to 2, this is on F, and 2 went right back to 1 on G. 2 goes to 3, and where does 3 go on G? Back to 2. I'm liking this. 3 goes to 4, which then goes right back to 3. 4 goes to 5, which goes back to 4, and 5 goes to 6, which goes back to 5. Do you see how on my little mapping that these two things match? Now, technically, I'm supposed to also check it the other way. Right? That's F going to, if I go F first and then G, this was actually G of F of X. Right? Because I started plugging in F and then went to G. I have to check F of G of X, which means I start on G. So 2 goes to 1, which goes to 2. 3 goes to 2, which goes to 3. 4 goes to 3, which goes to 4. 5 goes to 4, which goes to 5. And 6 goes to 5, which goes to 6. And we notice again, what I put in is what I got out. So each time, and this is it's called proof by exhaustion. That's the reason why it's called proof by exhaustion. I showed in every case f of g of x equals x and g of f of x equals x. In every case, assuming that I gave you all of the cases. So can we conclude that they are inverses of each other? Yes. How would I disprove it that they are inverses? Find one example where it doesn't work. What I put in, running through the composition, does not give me back what I put in. Okay? All right. Proving they are inverses graphically. What do you notice about the points up here? I have 1, 2, and 2, 1, 2, 3, and 3, 2, 3, 4, and 4, 3, 4, 5, 5, 4, 5, 6, 6, 5. I have if x, y is on F, then yx is on G, and vice versa. So what should I really say here? Because it's got to work both ways. What's the double implication? If and only if. Let's do the if and only if. If and only if, which basically means if xy is on F, then yx is on G, and if yx is on G, then xy must be on F. It has to work both ways. Okay, it's an if and only if statement. All right, so now looking at this, okay, now this goes into the idea of proof again. Okay, y'all could sit down back there. Okay, staying awake, at least that's a bonus. All right, if I plug -4 into F, what do I get? -4 gives me -4. So if I plug -4 into G, what should I get? -4. And if we check that, we will. If I plug -2 into F, I get -3. Okay. So I need to check. So I need to check if I plug -3 into G, do I get -2? The answer is yes. All right, so I'm going to leave the rest of just check these few points. Does me checking these 5 points mean that I have proven it is they are inverses of each other? No, I have the more points I check, the more belief that I have.
Wait, isn't like any number over infinity still infinite?
What does that have to do with this?
Because you can't like get more confident because they're infinite points. So
Right, I can get more confident, but I can never prove it for sure. I have more belief.
so isn't
I have more belief, but I'm not 100% convinced. All right, I'll pick this up next time. I'm going to stop the video.